Dr. Venegas, please start.
Okay, thank you very much indeed. Let me start by sharing my screen. Give me 1 second, please. There we are. Okay, hopefully you can see my presentation. Let me know if not. Well, this is my name, Salvador Venegas Andraca. As I was introduced, I work for Tecnológico de Monterrey at Campus Santa Fe. I'm the head of the computer science department. And I've been working on quantum computation for many years now. I began working on it in my PhD. That was my PhD topic at the University of Oxford back in 2002, which is when I started that topic and that research. After finishing, well, I won't talk much about myself, but just let me give you a brief overview of what I've been doing and the reason for being here with you talking about quantum computation. These are my contact details, and if you cannot get them now, don't worry, because at the very end of the talk, the last slide contains the same information together with this tiny URL as well as the corresponding QR. If you go to that URL or read the QR, you'll get to a folder in which you will find this presentation together with 4 more files. They have more information about the topics that I shall be addressing in this talk. So now let me start by thanking Alberto Maldonado and Dr. Francisco Calvo for the great opportunity of being here on talking with you, sharing with you what I know about quantum computation. So thank you very much indeed. And thanks to the rest of the staff, students, all the people who make this colloquium possible. I know very well because I've been organizing conferences and colloquiums and workshops and all these academic initiatives since I was an undergrad. So I know very well that it takes a lot of effort, initiative, usually, and of course, it's pro bono, which means non-paid initiative, effort, and work. That's the very soul of academia. We should make in the world, making a better world, making a better country, and I truly appreciate it, and thank you for doing that. Now, our sponsors, Tecnológico de Monterrey, is the organization. It used to be also CONACYT, but not anymore. The main funding organizations of the research initiatives that I shall be introducing to you in a few minutes. So that's me. That's a show. I won't talk much about myself, as I said. I just want to tell you that I began working in this field many years ago, doing my DPhil at the University of Oxford. And then when I finished at Oxford with a thesis on quantum walks and quantum image processing, I came back to Mexico. Back in 2004, during the very end of my PhD, I founded the field of quantum computation in Mexico, working with people from Simvestab or the Universidad Autónoma de Yucatán. We organized the first Mexican summer school on quantum computation and quantum information. And since then, we've been having and organizing several initiatives, including pro bono courses, as well as doing research, supervising graduate and undergraduate students, and so on and so forth. After my return from Oxford, I was here in Mexico for a year. I began building my group at Tecnológico de Monterrey. And then I went to Harvard University I was basically a visiting professor, but I mainly did postdoctoral work. Basically, I focused on research. And then I returned to Mexico, and I've been, as I said, working on a number of topics that I shall share with you in a few minutes. Okay, now I understand that this is one of the first talks of the colloquium, so I'm not that sure that many of you will be well acquainted with the basics of quantum computation. That's why I thought of having a concise introduction to the basics of quantum computation, to the mathematical, physical, and computational elements and arguments that make quantum computation an attractive field of research and investing, because this talk is of course about research, but it is not only about research. It's also about the development of a new emerging market in which many well-paid jobs will be produced, are being produced now, and will be produced in the near and midterm future. And that's very important, you see, because doing research, as Richard Feynman used to say, what's the reason for doing research in physics? Well, just for the sake of it, just for the pleasure of understanding and learning. And this is indeed true. But it's also true that countries, the people who fund research, either that money coming from public funds or private funds, they need to have more reasons than than just the pleasure of learning and producing new knowledge. That those reasons usually translate into the creation, the development of new markets, new high-tech markets, because with that, with the creation of those markets, new jobs come along. And that's very, very important, not only for the development of the economy of a country like ours, but it's also for the for the robustness and the strengthening of the social fabric in which we all live. See, that basically what that means is that in order to promote the idea of investing many years of our lives among young people in reading for a first degree and then possibly going for graduate studies, either masters or PhDs, there must be very strong and solid reasons, not only the sake of knowledge. We must also provide, good financial, economical reasons and social arguments for doing that, instead of devoting our lives or devoting the lives of the youth to other activities, some of them legal and some of them, unfortunately, in our case, in our country, not necessarily legal, in order to extract people from those activities and put them into the much better scenario of creating knowledge and creating technology. We must create jobs. That's why it's so important to do that. And this is why I'll be talking about this stuff, about these activities of the second half of my talk. There's some mic open. I don't know whether there's some ad, or should I, if anyone wants to talk, it's the time to do so. ¿Hay alguna pregunta o algo que, porque escuché un micrófono abierto? No? Okay, very well. So in order to talk about quantum computation, the first question that I think we should pose is what's quantum and what's computation? Because there are many ways to answer that. The one I would, before that, let me give you, let me say the following. Quantum computation is a multidisciplinary field, and that means that many people with different interests, with different motivations, come together to work in this topic. For instance, as for several theoretical physicists that I met during my DPhil, I realized that their interest was basically, for some of them in particular, for some very brilliant minds in theoretical physics like David Deutsch's, they were interested in making quantum computation an amenable testbed for analyzing different interpretations of quantum mechanics. So that's one of the reasons for doing quantum computation still nowadays, even though the field is transitioning into an industry field, applied research. The fundamental research done in quantum computation is of course related to the development of new algorithms, new hardware, and all the things that will actually lead to applied research and then to emerging markets. But it also has to do with the analysis and the understanding of fundamental and foundational ideas in quantum mechanics. So that's one reason for doing quantum computation. But in my case, I'm a computer scientist, and therefore I'm mostly interested, not uniquely, but mostly interested in the development of both hardware and software, that is to say, of the on the computer platforms and the algorithms that, based on the quantum mechanical properties of nature, will allow us to produce better results, better algorithms. The meaning of better here, as I shall address shortly, is several-folded. There are many ways to define better in the field of quantum computation. One of them is basically to develop faster algorithms. It's the best known, but not necessarily the only one. Okay, so I'll give you this definition, which is the one I like the most about quantum computation. And then, well, quantum computation is a field which is composed of an eclectic combination of ideas from quantum mechanics, from physics, and from computer science. Quantum mechanics, broadly speaking, and please, the physicists among you, forgive this sort of a kind of a naive, very experimental-oriented approach to the definition of quantum physics, but it's basically a scientific field focused on describing and predicting the behavior of matter and energy at very small scales. And by very small scales, I mean 10 to the minus 10 meters or smaller, okay? The size of atoms, the size of the size of subatomic particles, photons, and so on and so forth, right? And theoretical computer science is, well, it used to be a combination of ideas from, at the very beginning, of ideas from physics, engineering, and mathematics. But from a very early stage, theoretical computer science became a branch of mathematics focused on answering this question: what are the fundamental capabilities and limits of computers? And in quantum computation, what we do, I mean, operationally speaking, is to use the rules, the mathematical rules that define the behavior, that describe, the behavior of very small objects in order to produce hardware and software. Now, the reasons for doing that are many. One of them I just mentioned, which is the advancing or analyzing ideas from the foundations of quantum mechanics. But the very birth of quantum computation came from the following problem, which was the fact that running precise, that is exact and efficient computer simulations of quantum systems usually leads to an exponential, to algorithms that require an exponential amount of time to run. So I'll say it again. Whenever, well, not whenever, but it's generally the case that developing algorithms for running both exact and efficient simulations of quantum systems is an impossible task, or at least it is a task for which we know no solution at all. It's either exact or precise. Of course, as most likely many of you know, there are several subsets of quantum mechanical operations that can be efficiently simulated using a classical, that is to say, a digital computer. However, that's not, the whole cases that we can find in quantum mechanics. There are several experiments, several experimental setups, several phenomena in quantum mechanics for which, when we try to run when we try to design and run an algorithm that simulates that quantum phenomenon, those quantum phenomena, both precisely and efficiently, we have no idea how to do it. So it's either precise or efficient. When it comes to being exact or precise, then the trade-off usually that we have to invest an exponential amount of time. Okay, so that scenario has been well known by the community of theoretical and experimental physicists for many years now, for many decades. And it was back in the late 70s when Richard Feynman, among many other physicists, well, not many, among several other physicists and computer scientists in the United States, basically based at MIT and Caltech. But it was Feynman, the lead author of this idea. He asked whether it would be possible to use quantum systems in order to simulate other quantum systems. Hold on, I have a question here in the chat. I can't see it. I can't read the chat. I had one question here. So if you have questions or anything to say to me right now, please feel free to do so. Okay. Well, so I was saying, Richard Feynman then posed the question, given the difficulty or the impossibility, at least the practical impossibility of having both exact and efficient algorithms, classical algorithms, digital algorithms for simulating quantum systems, he wondered whether it would be possible to develop that kind of algorithms that is exact and efficient using a different kind of hardware, so to speak, a hardware whose rules, whose behavior were defined by the rules of quantum mechanics instead of the rules or the laws of classical physics. So this is when quantum mechanics and quantum computation had, I would say, the most recent adventure, because the links between physics and computation come from a long time ago. There are many algorithms that we used, say in optimization, for instance, like simulated annealing, that actually have a physical inspiration. Okay, so that's the introduction to quantum computation. This graph, tries to show the dramatic difference that there is between efficient algorithms, that is, efficient algorithms for which we need to invest just a polynomial amount of time to run them, in contrast to exponential or factorial time algorithms that really take a lot of time. Some take so long to run, and that even in many cases, the very edge of the universe wouldn't be enough for running these algorithms. So of course, that kind of algorithms, even though they produce results, they are fully practical, and we need to have better solutions for the same problems. Now, quantum computation is transitioning from an emerging branch of science into a mature research field, as well as an emergent branch of business. Okay, it's an emerging market. There are several fields in which quantum computation has had cross-fertilization, like artificial intelligence, machine learning, computational geometry, and image processing. It's also an ecosystem, an emerging market of advanced technology, where we can find investors, global companies, small to large companies, and governments. So you see, all the people who would actually be, who are required, all the organizations or the kind of organizations that are required to build an ecosystem in which sustainable growth can be achieved, are just right here and been in quantum computation for several years now. Now, let me get a bit technical about the differences, the mathematical and physical differences between digital computers and quantum computers, so that then we can talk about quantum algorithms. And that difference will be the one between bits and qubits. A bit, which is the fundamental unit for processing information, in digital computers, can be realized in many ways. We can use relays, we can use transistors, we can even use switches on and off manually, manipulated. But the point is that a bit is always no matter the realization, the mathematical description of a bit, it's always an element of a scalar space in which two elements are found, 0 or 1, or on and off, or happy and sad. Doesn't matter the labels that we use. What matters is that these two labels refer to two mutually exclusive states of the actual physical system that we use for implementing a bit. Okay, so a bit is an element of a scalar space in which we have two elements. We can label as we may wish. Now, a quantum bit is a vector. Okay, now this is just to remember my kind of say childish way to talk about a vector. Remember that we can draw it, we can actually write it as an ordered pair, or we can write it as, and this is not the childish, we can write it as a linear combination of an arbitrary basis of the vector space in which we are working. And a qubit is basically a vector defined over a vector space in which we use complex numbers. So mathematically speaking, that's what a qubit is. It is a unitary vector, meaning of length 1, in which we're going to use complex numbers as coefficients of an arbitrary linear combination that we may have for describing a qubit. So now you may actually start realizing some of the mathematical differences between bits and qubits. It's not only that qubits are vectors, but also that we use complex numbers. And with complex numbers, there comes different mathematical machinery in which we're going to have different parameters. We're going to have different ways to represent a vector, for example, using Euler's formula. And then that will provide the basic mathematical richness of the fundamental units of processing information, processing, that we have in quantum computers. Okay, that together with the mathematical formalism that we use to combine qubits, which is the tensor product, is the very foundation of the mathematical richness of quantum computers. And we use a particular notation to refer to qubits. Instead of using the typical arrow notation, we're going to use the line with something, the vertical line, with something that looks like a greater than symbol, and we're going to call this a ket. K as in kilogram, E as in Edward, T as in ton. Okay, so this is a ket. There's another symbol very frequently used in quantum computation, which is a bra. It's like a less than symbol together with another vertical line. So this is going to be called a bra. And using the ket and bra notation, also known as the direct notation, thanks to the due to the man who invented it, who was Paul Dirac. The use of kits and brass is not only a different way to write mathematics in quantum mechanics and computation, but it's also, I mean, the reason that Dirac had for inventing this notation was that it greatly simplifies all the computation that we have to go through. That for those of you who are interested in getting into the field, you'll soon realize much sooner than later that the amount of computation that we have to run is just huge, really. Actually, it's exponential, okay? But there are ways to simplify it. Very well. Sorry, so this is the general definition of what a qubit is. And let me see what time it is. And as I said, it's a vector that can be written as a linear combination of an arbitrary basis, where these numbers, alpha and beta, are complex numbers, okay? And the any qubit must be unitary. That is to say, its length, its norm, has to be equal to 1. Very well. We can also write, there is a visual way to represent qubits, which is by using the Bloch sphere, the one we have here. And I won't dwell into this because we don't need it, for the rest of the talk. But just keep in mind that in many cases, this is a very convenient way to write a qubit, because we make explicit mention of the parameters that we can use for processing information in a quantum system. Okay, now let's talk about quantum algorithms. I say fast and furious, as in the movie, because we want them to be fast and furious. Well, at least fast, furious, hopefully, okay? But let's see whether we can do it fast. Now, the word fast in digital computation or classical computation, and let me say this. When I say classical digital computation, it's because in quantum computation, we refer to any other kind of computation as classical computation. That, I have to say, it's a bit of an abuse of the language, because in physics, any branch of physics which is not quantum physics is usually referred to by the vast majority of colleagues as classical physics. Okay, so this way of this rationale is translated, exported into the world computing. And then we tend to say in quantum computation, classical computation, to refer to any computation which is not quantum. That is a bit misleading, I have to say, because back a few decades ago, there was a branch of computer science that was kind of abruptly stopped because of political reasons, which was analog computation. And in analog computation, we can find some of the results that we have in quantum computation kind of in parallel, okay? And those results just can't exist in digital computation for the simple reason that we're working with discrete systems instead of continuous or dense number systems, okay? But I'm sorry for the use of the language, but that's just the way it is in the field. So whenever you hear classical computation or digital computation, we basically mean the same thing, even though they may not necessarily mean the same thing. Okay, so now going back to this slide, the definition of the word faster in digital computation actually has at least 2 meanings. The first one is taking advantage of the properties of the hardware in which that we've been given to run an algorithm. For instance, if we have, say, an old computer with a processor that runs on a serial basis and has no parallel circuits in it, it's just one simple CPU, then all we can do is to run any algorithm serially, sequentially, okay? However, if we have, well, not so modern, but is a modern CPU in which we may have cores, we may have pipelines, or we were given a parallel computer or a cluster of computers, then we could actually take it, well, if we are good at programming, if we are serious programmers, then we must take advantage of the properties of the hardware that we've been given in order to run algorithms as efficiently as possible. Okay, so for example, if we have a problem like a matrix multiplication, in which we can run in parallel several computations, and we have access to a parallel computer or to several CPUs or to pipelines or different cores, then we're expected to do to take advantage, to make full use of that of the properties of that hardware, right? Now, that idea of making proper use of the properties of the hardware that we've been given access to, is also found in the field of quantum computation. And that actually has been the main focus of the research that has been performed since the birth of this field. That is to focus on the properties of the quantum hardware that we are given access to, in order to determine, to find novel ways to develop better algorithms, which in this case would mean faster. Okay? And hold on, let me use the annotate. Yeah, here we are. This mathematical say process that I describe here is something that we know in quantum computation as quantum parallelism. It really doesn't matter now to focus on the particular mathematical details of this process. I just want to focus on the following. Here I have n different qubits. Remember, the ket notation is used to mean a ket. So it's used to mean a qubit. Okay, so I have n plus 1 qubits. Okay, so I have n plus 1 qubits that I'm gonna make go through n plus 1 different gates. So this is the notation that we use, h with the circumflex sign, to mean a quantum gate. A quantum gate is, conceptually speaking, is like a classical gate, like the AND gate or the NOT gate or the NAND gate, in the sense of having some input and producing some output. Okay, so the rationale of a quantum gate is exactly the same. The main difference between classical gates or digital gates and quantum gates is the mathematical description of their behavior. Okay, but conceptually speaking, they both have the same behavior. They have some input and they produce some output. So here we have n H gates, H Hadamard gates. That's the symbol that we use to mean that particular gate in quantum computation, together with the identity gate. Okay, so basically here we have n plus 1 qubits that are going to will go through n plus 1 quantum gates, like having n bits and they can go through a number of gates. In this case, it would be n gates. Okay? Now, the point here, and pay attention to this, is that after making the result, the outcome of making n plus 1 qubits go through n plus 1 gates is a summation in which we have an exponential number of components, which I would say must sound weird. Because how come that by having a limited amount of hardware, we have an exponential number of different components of anything as a result of combining gates and qubits? Okay? And the answer to that question is that this is due, first of all, this is right, okay? This is 100% correct. And this is due to the vectorial nature of qubits and the way the quantum gates are applied to them, okay? Now, the second and last summation that we have here is basically applying a gate which computes the function f over the elements of this summation. And the result of these two steps is the summation in which we have all the values that correspond to the codomain of f for each one of the elements of the domain that go from from 0 to 2 to the nth power minus 1 in discrete steps. Okay, in the discrete set of these numbers. So by means of 2 steps and a polynomial amount of hardware elements, we've been able to produce a mathematical expression that contains an exponential number of different values for this function f. Okay, the way we retrieve information from a quantum computer is a different matter. It's a topic that I shall not get into now because it's very controversial, not in the sense of whether it is true or not, in the experimentally speaking. Here comes the complexity of the thing, but because it's hard to explain in just a few minutes. Okay, but the point that I want to make is that by doing this, by running this expression that we know as quantum parallelism, all we're doing is basically to make proper use of the mathematical properties of the hardware that we've given access to, okay? So that would be the equivalent of writing a program that takes advantage of the different pipelines or the different cores or the GPUs or whatever hardware we have in place in order to run parallel versions of a program that can be actually parallelized, right? Now, we would hardly get a Turing Award for doing things the way I just described. That is to say, making proper use of the hardware we've been given access to is only to be expected, you know, from a serious programmer. Now, the next, and that's one definition to make things faster. Now, another way to make things faster, which actually comes with a lot of ingenuity, is based on this first definition of faster to develop ingenious algorithms. For example, in classical computer science, we have the TSP, the traveling salesman's problem, which is a paramount problem, NP complete, NP hard. All computer scientists here have had to dream and maybe have nightmares with this problem several days. And if we try to solve the TSP using a brute force algorithm, we can certainly solve it. The only problem we're going to face is that the complexity of the brute force solution to the TSP is of factorial order, which is, of course, unacceptable. Now, one of the best algorithms known so far for solving the TSP is known as the Bellman-Held-Karp algorithm that has this complexity, which indeed is not efficient because it's exponential, but it's much better or much less worse, so to speak, than the brute force solution in terms of computational complexity. Now, the Bellman-Held-Karp algorithm has some of the most famous surnames in computer science. So the development of this algorithm wasn't trivial at all. As a matter of fact, coding it is not trivial at all. It's difficult to code. So the point I want to make is that designing ingenious algorithms is a very difficult activity, which in fact in quantum computer science is closely related to the difficulty of designing quantum experiments. But the point here in this slide is that the design and the coding and the implementation of ingenious algorithm in quantum computation is a field which is really full of open opportunities, okay? So if you feel like going for a PhD in quantum computation, this is the place to go, or this is one of the places to go. Okay, I'm gonna hurry up because there's a number of things I wanna tell you, and I'm running out of time. So building quantum algorithms is challenging because we need a complex and interesting problem. Quantum mechanics is a counterintuitive theory, which we really need to invest a lot of time. I mean, not many years, but we really have to make a serious effort to grasp the basics, the foundations of quantum mechanics. And also that a competitive quantum algorithm must not only produce, must not only be robust in the sense of doing what it is expected to do, but it has to be better than the classic algorithms developed at least so far. By better, it usually means faster, but could mean at least for some input values. So designing quantum algorithms is fantastic. It's a lovely experience, I have to say, but it's challenging. Okay, so worth a PhDs. Okay, there are several methods to write quantum algorithms. One of them is what I just described, quantum gate-based circuits. Okay. And the main difference between the digital circuitry that we use for, say, for the lower part of this slide with the circuit, and the one that we have, the quantum algorithm that we have on the upper side of this slide, is the mathematical description of the gates that we use and the inputs that we have, the bits and qubits that we have for those circuits. Okay, so learning the mathematics that describe these two systems, particularly learning the mathematics that describe the behavior of quantum mechanical system, is a must for computer scientists who are interested in getting in this field. Okay, the mathematical machinery we use in quantum computation is not distant, but it's different from the one that we are usually taught in a typical syllabus in computer science in any part of the world. So learning this requires effort, requires additional strength and input, but that's what we computer scientists are made of, strength and will. There's another way to write quantum algorithms, which is by using a differential equation. This is the most famous Schrödinger equation. And This requires learning. You see, it depending on the school of thought of the university where we study. It could be that the computer scientist or a computer engineer had access or were expected to take courses on differential equations. But if not, in order to learn quantum computation, and in particular to learn the the models of quantum mathematical computation and quantum annealing, it is really important to learn the basic, at least, of differential equations. So that's a point. And this is a third and quite new method for developing quantum algorithms, which is known as variational quantum algorithms. It's basically a hybrid. It's a combination of ideas from classical computer science, machine learning in particular, and quantum computation. There's a number of different platforms that we can use for programming quantum computers, but basically the paradigm now is that, sorry, we have a classical interface and classical programming language like Python, C, C++, etc. And then, depending on the vendor, depending on the properties of this hardware and software, the machine or the quantum computer we're interested in using, there will be different APIs that we can use in order to send data to the corresponding quantum computer, and then to get data back as a result of the computation run on the quantum machine. Okay. There's also a lot of digital simulation software that is software that allows us to simulate the behavior of quantum computers, not necessarily efficiently, as based on the rationale that I described at the beginning of this talk. Okay, but there's plenty of information, there's plenty of platforms now to experiment and to learn to become an expert in this field. Now, applications of quantum computing and quantum technology, there are many. I'm going to mention just a few. The quantum teleportation protocol. As far as I understand, there will be a talk on one of the incoming talks in this colloquium, in which we'll be addressing the scientific foundations of the results for which three scientists were presented a Nobel Prize in physics this year. And one of them is Alain Aspect, whose photo is just coming, okay? But this is, I mean, the quantum teleportation protocol makes use. Yes, go ahead. Hello. Hay por ahí un micrófono abierto, no sé si quieren hablar. Okay, I don't think so. Okay, guys. So this is one of the first protocols developing quantum computation. This is really important, and this protocol is very important. It's paramount for the development of quantum networks, and in particular of the quantum internet. And the best book that I know about the quantum internet was written by this very good friend of mine, Peter Roth, and I strongly recommend you to read it. Okay? Fantastic book. Two paramount applications, two very well-known algorithms coming from the quantum realm are Grover's algorithm and Shor's algorithm. The first one used for finding information in disordered data sets, and the second one for basically for finding periods in Shor's algorithm that, I mean, whose main application is factorizing integer numbers. That is to say, it's an algorithm that allows us to have an efficient algorithm, and therefore an efficient implementation of the fundamental theorem of arithmetic. Okay? Shor's algorithm is very, I mean, both algorithms are really important because they basically represent a hallmark in the development of quantum computation. Shor's algorithm in particular is very important nowadays because several public key cryptographic protocols could become vulnerable and will become vulnerable in the following years due to basically due to using Shor's algorithm on robust enough quantum computers for breaking those codes, those protocols. Okay, so that's it. This is a paper that I wrote with colleagues from the Inter-American Development Bank, and at that time the Cambridge Quantum Computing Company, now known as Quantinuum. And the goal of this paper was to show, I mean, given that Shor's algorithm will represent a threat to certain cryptographic protocols, in the following years, then the question that we pose is whether it was possible or not to use quantum technology to protect those protocols that shall become vulnerable due to the attack of quantum computers using Shor's algorithm. And this paper is an answer to that. The answer is yes, we can use quantum technology to provide an additional layer for protecting protocols that shall become vulnerable due to the attack of quantum computers. This paper is in the folder that I share with you, and that will be giving you again the tiny URL and the QR code shortly. Quantum key distribution is another very good example, paramount example of quantum computation and quantum communication. This is an aspect, one of the winners of the Nobel Prize for Physics of this year. Quantum simulation of physical quantum phenomena is also a very, very relevant field. This is just a drawing representation of a globular protein, and using quantum algorithms to simulate, to replicate the behavior of physical systems, and in particular biological system, is a very important, crucial, I would say, field for the development of quantum computation, and showing that quantum computing is a field that must be pursued, that must be nurtured for the benefit of mankind. Solar energy systems is another example of a field in which we can use quantum computers to simulate corresponding quantum effects that we need in order to have better materials for this field. This is a paper that we wrote in my group about how to use particular kind of quantum algorithms known as quantum walk-based algorithms for analyzing biological data, which in the case of this paper was the analysis of genotype networks. This is one of the main topics in my research group. This is the first paper that we wrote along these lines, and now we have now it's become one of the key topics addressed in my group. So if you feel like combining quantum algorithms and in the analysis of biological information, then come along. Shall be more than happy to welcome you in our field, in our group, sorry. Quantum machine learning is another topic that has become really, 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 really exciting over the last few years. There's information here that you may be interested in, but basically, the first link, I would say, one of the early justifications for the development of this field of quantum machine learning is found right here. We can develop quantum algorithms for solving combinatorial optimization problems. Quantum annealing algorithms are particularly prone to that. They were designed to do that, okay? But this is not the only platform for doing that. We can solve combinatorial optimization problems using any kind of quantum algorithms, okay? So that's, on the one hand, this would go for, say, this part of the correspondence, meaning the relationship between combinatorial optimization problems and quantum algorithms. On the other hand, for those of you who are interested or knowledgeable of quantum machine or of machine learning, you know that it's typically the case that the translation of a machine learning problem into mathematics and then into computer science transforms or requires the definition of a cost function for which we need to find a minimum or a maximum value, okay? Meaning we need to solve an optimization problem when a machine learning problem is translated into mathematics and computer jargon. So this is the link. The link is combinatorial optimization problems that are required to be solved on the one hand, machine learning, and that can be solved using quantum computers on the other hand. Very well, quantum machine learning is in its infancy, but it's a huge, really huge growth. I don't want to say the expression exponential growth, because I find that I don't like it to use, okay, because it's a bit misleading. But nonetheless, it's just huge. Many groups are working on this, so this is very hot this morning here in many parts of the world. So you're thinking of pursuing a PhD in this field. It's very sensible, to go to work on this in this topic. And as a matter of fact, I understand that Catalina Albornoz will be talking about this. We'll be talking in this colloquium, and the company she works for, Xanadu, is one of the most important organizations in the development of software for solving optimization problems and quantum machine learning problems nowadays. So, well, there's a number of things that we'd like to talk about in quantum machine learning, but now let me focus on the very last part of this talk, which is quantum computing from the lab to the market. So as I said, quantum computing now is an ecosystem in which we find investors, global companies, small to large companies and governments. These timelines, I got it here for one reason. I want to show you how new this field is and therefore how full of opportunities it is. These 8 scientists are well, not necessarily all, the fathers of quantum computation, but they are a very good sample of the fathers of quantum computation. Their names are compulsorily found in any book of the history of quantum computation. Now, as for these 8 scientists, 7 of them are not only still alive, but they're also working. They keep on working. They're active in the field. David Deutsch, Pierre Shore, Love Grover, Nishimori, Di Vincenzo, Aharonov, and Farhi are still working in this field. And what I mean by field is not that they are at the very end. They're not necessarily at the end of their career. They're very actively working in quantum computation. The only one of these 8 scientists who's just passed away, who passed away a few years ago, is Richard Feynman. And you see, the point I want to make is that since the fathers of this first and second generation of quantum computation are still alive and working, that can gives us a very good idea of how young the field is, and therefore how full of opportunities it is indeed. Now, these are some of the examples of the companies that are in quantum computation, a lot of money coming with them, and therefore a lot of opportunities. As for the small to large companies, I would like to mention Canada, of course, that I just did. Quantum South is as far as I know, the only example that we have in Latin America as for a quantum computing company. Quantum South is mainly focused on the development of quantum algorithms for optimization problems. I got the pleasure, the honor, and the privilege to know their founders and to work with them on several projects. So it's a company that we have to keep an eye on because they're very good and they're going to do great things in the near future. Cureca is the first company focused on building the links or building bridges between the technical field of quantum computation and human resources. How to find a job in quantum computing? If you're interested in that, speak to Cureca, speak to Araceli Venegas Gomez. We shared this shrine, but as far as I know, we're not relatives. Yes, Luis, go ahead.
Yeah, thank you, Doctor. Actually, my question was regarding the last part, what you mentioned about the status of the current quantum technology. So in my understanding, tell me if I am correct, we are in the foundational, in terms of mathematical definitions, in terms of the beginning of this technology, right? We are not ready to do the next steps, having some product finance for the people in general. We are creating still, we are still in the foundational of the quantum technology, right?
I wouldn't say so that, let me state what I want to say. We are, on the one hand, there are several groups heavily working on the foundations of quantum computation, indeed, both theoretically and experimentally. Mainly experimentally, because there are several challenges that are still to be overcome. But the field is not in its infancy anymore. There are several companies, and that's an interesting thing to say because, you see, when research is university-based, it is, of course, very interesting. It is, of course, very passionate to talk about. But the problem of academic research is that it may not necessarily have the money and the human talent required to go from prototypes into products that can actually be sold as products or services in the market. For that, we need companies, okay? And the good news here is that there are several really big companies, global companies, that have been putting money in this field for at least 10, 15 years, and that are now giving access to their systems, okay, like IBM, for instance, or IBM is the best example, I think, in which people can learn, people can practice, okay, and then people can actually use it. I mean, use these platforms, for building high-tech products. Now, it also has to be said that the development of quantum computation nowadays is, in my opinion, and in the opinion of many other colleagues, equivalent in terms of technological maturity to the development of mainframes, of digital mainframes that we had back in the late 60s or early 70s of the last century. So that would be, in my opinion, kind of the right parallel to do. The machines that we have now in quantum technology are equivalent in terms of technological maturity to the ones that we had, to the digital machines that we had as early mainframes back in the late 60s or late 70s of the last century.
Okay.
So that means that there are many things that we can do now. For example, there is a very intense research, applied research in the field of new molecules, okay, for pharmaceutical companies. But we need to do that. I mean, we need to keep on working on the hardware that we have now, even though it's limited because we don't have, for example, full quantum error correction, okay, and we don't have as many qubits as we would like to, and we don't have all the fidelity that we would like to have in qubits. I'd say, broadly speaking, what that means is that we don't, the information that is stored in qubits now is there and is intact just for a very short period of time, okay? So we need to increase those parameters in order to make quantum computers more robust. But the point is that we have that hardware now, and we need to make cases, successful cases of applications in order to motivate the companies that are investing millions and millions of dollars in this field in order to keep on doing that, in order to improve their hardware and make this a fully successful ecosystem. Okay, so that's basically my view about this field. We are not in the infancy anymore. We are sort of in this first jump towards becoming a fully scalable, emerging high-tech market.
Yeah. Thank you so much for the answer.
You're very welcome. Thanks a lot.
Pero por el
Yes.
momento tiene una pregunta, si puede compartir el enlace de todos los recursos que usted ha.
Sí, lo voy a hacer en un momento. Ya voy a pasar a lo último. Okay, this is the very last things I want to say. These are some reports that one of them I've been working on the World Economic Forum. The World Economic Forum. Sí, adelante, por favor.
We are over the time. With respect with the next lecture, we have to prepare the room.
Okay, that's fine. Just keep in mind, the World Economic Forum, take a look at the documents that I shared with you, okay, in particular to the quantum security one. I'm a co-author of it, not because I'm a co-author, but because it's a very relevant topic now. This is our Quantum Information Science Technology Latin America Facebook wall. Join it if you feel like. Keep in mind that we have Quantum Latino on its third edition next year in June. So Quantum Latino is the largest quantum event in Latin America. Some of the speakers here have also been speakers in this field, in this event. And finally, thank you very much indeed for your time and kind attention. So these are the contacts. These are many ways to contact me. This is the tiny URL I was referring to right here, okay, as well as corresponding QR code.
Okay,
I don't think that we have time for one more question. So if you want to get in touch with me, feel free to do so either by sending me an email or any other means. I'll be more than glad to answer any questions you may have later.
Time for one last question. Anybody have a question? Okay, doctor, thank you for your lecture. We will wait for the link of all resources you have shown this presentation.
Okay, thank you very much. Have a great day.
But the same. Doctor Cristian, ¿está presente?
Hola, ¿me escuchas? Hola. Me indicas si me escuchas, por favor.
Sí, se escucha, pero se escucha un poco bajito.
Ok, esperamos un momento que nos den, que inicie la grabación y entonces les voy a presentarlo.